Okay, we are starting one more time. Diana Ortega now is going to talk to us about the calculus of economic stimulus packages. Take it away, Diana.
Okay, so we first start off with a scenario that states that our rich aunt gives us $10,000, no strings attached. If you are like most Americans, you will save 5% of the amount given, which means you will spend 95%. The money that is not saved is spent on things like food, entertainment, or anything else you could buy with it. So the money you originally spent is spent again and stimulates the economy through something called the multiplier effect, because obviously when you buy something, that money is used to pay off a worker's wages and they continue to spend that money on whatever they want. So like the scenario above, the governments provide economic stimulus to have the same effect as that rich aunt's gift. They do this by offering tax rebates or refunds, and this is supposed to lead to economic growth. So throughout this presentation, I'm basically just going to show you the math behind these stimulus packages and kind of how they relate to today. So we first begin with the original amount given, and what we could do with this is figure out how much of this amount is going to go into the economy based on the idea that 95% is the spending rate. So what you would do to figure that out is basically just multiply the amount given times the spending rate, which in this case is 95%. And you could do that for the following months to just figure out whatever month you want to figure out the amount for. So this is something like this table can also be shown in something called a geometric series, which we see here. This $10,000 is can be factored from the above table, and it's also the original amount we started off with. And then here we have this 95%, which is the rate at which money is going into the economy. And then the K here just represents the time. So you could plug in whatever month you're looking for to try and figure out how much money is going to go back into the economy. And this is basically just another way of writing this table, kind of an easier format. So another thing we could do is figure out the economic impact of whatever month. So I took this from our calculus textbook. This is kind of another way of writing out the geometric series I wrote before, just like an elongated version without any numbers. One thing you can do is multiply by r and then subtract the second equation from the first equation. You will see the middle terms cancel out and you will just be left with this here. After that, you can just factor and then solve for S sub n, and you will get an equation that when you plug numbers in, you would be able to find the economic impact for whatever month. So that is what I did here. I just plugged in whatever month, 1, 2, or 3, or 4, and however many months you would want to plug in. And this is the economic impact for that certain month. So another thing we could do is basically find out the total economic impact. So this here is used in geometric series. It's used to find out where a series converges to. So here what this amount would converge to, or like the economic impact, would be $200,000. So one thing you can see from this is the greater the spending rate, this R means a greater economic impact. Obviously, if you put 98% of your money into the economy, then you should get more of a reward, or like more money should be circulating in the economy. So here I just wanted to show previous and current stimulus packages and basically just reinforce the idea that the spending rate is impactful. So if 20% of the people who received stimulus packages in 2008, where there was like a bit of a recession, and 32% put the money into their savings, then obviously there's not as high of a spending rate. So that's probably why this recession kind of lasted until 2009, where it finally started growing again. And as you may or may not know, we also have a 2020 stimulus package, and it's obviously a lot of money involved to try and get a lot of reward back as well. So then I just included some controversy, which is based on the 2008-2009 stimulus package. This is just some ideas that people had. People think that some reasons why these stimulus packages don't work, in their opinion, is because they do not address the root of the problem, which is kind of true because these stimulus packages, they're more of a temporary solution, but they are still meant to help the economy. And then finally, some people think that these packages don't have any economic benefit, but as you have seen, if you do put a good amount of money into the economy, then you should get some reward back. And here are my sources, and thank you.
That was really good, Diana.
Thank you.
Yeah, can I ask a question?
Yes. Yeah, leave it at Diana because I want to ask one too. Go ahead.
I have two questions. One's for both of you and one's for Diana. Diana, I thought it was really interesting that you started the presentation by talking about the rich aunt. Is that your rich aunt or who's?
No, it was just a
Does-
scenario, and
Okay.
the presentation was just based off that idea.
I was having a little jealousy there because I don't have a rich aunt that has given me 10. Actually, I do have a serious question. You mentioned that, you know, it's kind of common for if you get $10,000 and you weren't expecting it, and maybe you were thinking, hey, I'm going to go spend 95% of it, but which I think what you really sort of pointed out was that 95% means something to a lot of people.
Yeah.
And the other thing I thought about when you were showing the 2008, you mentioned that 32% of the stimulus money was put into savings. And I guess my question is, do you think it makes a difference if someone, what kind of difference does it make? Let's say that I was one of the 32% that put it into savings, but I didn't put it into a treasury or like a bank account that just sits there. I put it into stocks and mutual funds, and which represent direct investment into a company that then can turn around and spend that money on additional employees, equipment, product development, and so forth. How does that factor into someone that, quote, doesn't spend it on retail or entertainment, but they spend it on buying stock in a company that then turns around and uses that money to grow and develop?
Well, I don't think you necessarily have to buy the typical things to get an economic impact out of it. If you invest it and the money is still circulating in the economy, I think that's still beneficial because at the end of the day, there's still more money in the economy.
That makes me feel so good because I was worried, because that's probably what I would have done, and I was worried you were going to label me as a hoarder. But since I usually put it into an investment, then I can still cross the box that
you're still
I'm a
doing
good
good.
person. Okay.
Yeah.
I feel like that was a trick question, Dr. Illich.
That was not a trick question.
Do you have
Oh, I got one more question for both of you. Has this exercise, how do you think it's helped you in terms of your thinking about things? Maybe when you hear things in the news, has this helped you maybe question some of the claims that you're hearing, just general claims about this doesn't work, or this stimulus package works, or this is what the virus is doing? Has this court class helped you think a little bit deeper and question things a little more?
Yeah, I think so. Because obviously, especially with like the president, not everyone agrees with any president, and there are people who kind of always try to take things away, make them seem like they're bad, but obviously there's math behind these things, and I mean, what's more concrete than math?
purpose, and this can be modeled by the exponential function of unlimited population growth. And so this process does not include people who leave or come into the community. It doesn't include any social distancing measures or vaccination or anything like that. So you can derive this equation by setting dy dt equal to ky. And k is just your rate constant. And so you can multiply the y over to the left side of the equation and then integrate both sides of the equation with respect to t. And so we learned earlier this year that the integral of 1 over y is the natural log of y. And then, of course, you add your c to the end like we do in every integration. And then you can set each side of the equation up to the e. And so that cancels out the natural log on the left side. And then on the right side, you have the e to the kt plus c. And so using the exponential rule, you can pull these two e's apart and have e to the c times e to the kt. And then to get rid of the absolute value bars, you do the plus and minus on both sides of the equation, or on the right side of the equation. And then the plus and minus of e to the c can just be looked at as any variable. And so for this, it's just y naught. And then the a is just there as like an intermediate variable. So the derived equation is y is equal to y naught e to the kt, where y naught is the initial population, t is the time, and k is the rate constant. Okay, and then so pertaining to COVID-19, March 1st began with about 100 cases in the United States. And as of April 14th, there are 601,472 confirmed cases in the United States and 1.9 million cases worldwide. And so I added an exponential graph of both the confirmed cases in Texas and the confirmed cases in the world. And I got these graphs from Johns Hopkins and from their data. And so I decided it'd be interesting to find the rate constant for the rate of the spread of the virus for the United States. And so you can do this by having the initial cases at 100 and then the total population at 601,472. And so to find k, you set both sides using the natural log, or you find the natural log of the, what did I do there? Yes, okay. So we did the natural log, and then you found that k is equal to the 0.1978. So that's pretty large, that's 20%. And of course, this isn't an exact number. The actual value of the rate constant is probably a little higher than this because of the fact that this is not accounting for outside factors. And so you can use this to kind of estimate and calculate the full effect of the coronavirus on the United States. So it is interesting to know that this isn't going to continue forever, the unlimited growth of the virus. And so it will eventually turn into the logarithmic growth model. And so it basically is going to have a limitation. And at some point in time, the maximum number of people will become infected, or we could be practicing social distancing, or a vaccine could become available. And so on the bottom left side of the screen, I inserted the logarithmic growth of COVID-19 cases in the world, and you can see it's already trying to flatten the curve. So before this assigned project, I did not know that the exponential growth formula was derived from the dy dt, or the integral of dy dt. And it's very interesting to see how this pertains to our everyday life and that calculus can be used in this aspect. It's also very reassuring to know that it won't be just unrestricted growth for the rest of time, and that we will eventually have a curve off where as people recover and as other factors come in. And here are my sources. Thank you.
Very good. Thank you. All right. So here we are back. We're at Virtual Scholar Day, and I have a couple more students that have come in. We saw Teresa's great project on the spread of the virus, and Diana's great project on the stimulus package. And now Charlene is going to talk to us about thermal expansion, and Tristan is here for support. He will be doing his project with his partner on Monday evening. So again, Teresa is a dual enrolled student here at McLennan Community College and at Texas A&M. She's a biology major. Diana is a dual enrolled student in her high school, her local high school, and at McLennan Community College. She is a senior and will be graduating with an associate degree at the end of, in May, right? Or I guess, yeah, probably May, yeah. Charlene tell us about you.
So I am attending MCC to obtain an associate degree in civil engineering, and I work full-time at TxDOT as a construction records auditor.
All right. And Tristan is a computer science major, and he is also plays the French horn, studies the French horn at MCC. Okay, so take it away, Charlene.
So good morning, everyone. My name is Rindy Drews. I technically it's Charlene, but I go by Rindy. And I'm majoring in civil engineering. Today's presentation is thermal expansion. The purpose of this presentation is to realize that the effects of thermal expansion can be seen in bridges, sidewalks, railroad tracks, houses, oceans, weather systems, and hot air balloons. But it can also be seen in little things like canning jars or O-rings in a spacecraft. We will review some of those effects and how the dependence of thermal expansion on temperature, substance, and original length is summarized within an equation. So under ordinary conditions, there is no normal direction for substances to go. They are free to expand or contract, which changes the overall size, proportions. However, the proportions actually stay the same. The first formula is based on experiments and summarizes the dependence of thermal expansion on temperature, substance, and original length. The second equation is the linear approximation and is the one commonly used for practical purposes. This table is representative values of the coefficient of linear expansion. The delta in the linear equation can change based on the material. This is just a small portion of the types of materials that can be used in the equation. We will be looking at the steel coefficient. This example is just to give you a visual perspective of how metal, such as steel, moves when the temperature changes. Figure A is showing the steel strip is straight at the starting temperature and the two components have the same length. Figure B shows what happens when the temperature gets hotter, when the temperature gets higher or hotter. The strip bends to the right since the steel on the left has expanded more than the metal on the right. If the temperature got lower or colder, the strip would bend to the left. On our next example, I will show you how the equation can be used. This is the Golden Gate Bridge in San Francisco. It measures 1,275 meters long at its coldest temperature. The bridge is exposed to a range of temperatures that vary from 40 degrees to below 15 degrees Celsius. If we assume the bridge is made entirely of steel, we can look at the change in length between these temperatures. The equation for linear thermal expansion can be used to calculate the change in length. I located the steel coefficient and multiplied that by the length of the bridge at its coldest. Then I multiplied that by the change in temperature. 40 degrees to below 15 degrees is a change in temperature of 55 degrees. So a bridge can extend by about 0.8 meters with a temperature change from below 15 degrees in the morning to 40 degrees in the afternoon. The change is a very small fraction of the length of the bridge, but this change is observable and is generally spread over many expansion joints. Because of that, each expansion joint has a very small change. If you are in the field of engineering or design, Don't forget about the little things that may have an effect when they have thermal exposure, like what happens if individual parts get really hot or really cold. You may recall the Challenger disaster that was blamed on O-rings. The destruction of the Challenger and its seven-member crew was an accident that may have been prevented if proper engineering reviews had been done on all parts of the Challenger. The rubber O-rings in a booster joint had been stiffened the day of the launch due to low temperatures. The stiffness caused the O-rings to not maintain the seal. That poor design opened the gap the rings were supposed to seal in the first second after ignition. It could not contain the pressure of hot gases produced by burning rocket fuel. Flames burned through the booster wall, causing the booster to tear away from the external tank. The tank ruptured and spilled highly flammable liquid hydrogen and liquid oxygen. Before I close out, I have a little fun fact I'd like to share with you. If you run hot water over a tight metal lid on a glass jar before trying to open it, it actually does work, sort of. The lid expands more than the jar with the added heat, and that's because metals have a higher coefficient of expansion than glass. That should make unscrewing the lid easier, but in actual reality, if you get the lid and jar wet, you more than likely are going to have issues gripping them. So in conclusion of my presentation, I'd like for you to remember that thermal expansion or shrinkage is actually all around us. From the bridges to the railroad tracks, to jars in your refrigerator, and even the little O-rings on a spacecraft. Luckily, there's an easy formula that we can use that may help us to avoid catastrophes. Thank you.
That was very good.
Thanks.
Do we have any comments from the group? Any questions or comments?
Well, that was just really good. I wanted to say I had to miss it for a little bit. I had a family thing.
You jumped out for a second. That's okay. We didn't see. So, I guess what made you? Why were you interested in this particular project?
So my husband, I work for TxDOT, and the office I actually work in construction, but at the district office, and we actually have the district lab right beside us. So I see material all the time. And I know the effects of heat in the field on bridges, or, even getting the asphalt too hot on the roadway has an effect on materials. So that pulled my curiosity in it. But also, as I said, my husband works for the railroad, so he's in maintenance, and they constantly have to go cut the track because it expanded or it shrunk or it cracked or whatever. So they have to constantly go out there and maintain the railroad tracks due to either the heat or the cold. So that kind of triggered my brain as, you know what, this would be cool. Because whenever I went over the index of what options we could do the presentation over, that was one thing that I was like, this could be interesting. So
good. Yeah,
that's my reasoning.
That's good. I think it was very fascinating. All right.